Physics 35 IB students. We are on our last unit, or our last topic. We're going to start by looking at energy, which is going to be a review. We're going to look at power, which is going to be a review. And then we're going to get into climate, which is pretty prevalent in all our lives today. So there should be quite a bit of material that you're already familiar with, either from Science 10 or just from the news or your own research, whatever it might be. There's going to be a lot of overlap to what you already know, but we're going to try to spice it up a little, give it a little physics extra flavor, and hopefully you can learn something interesting about the world and the climate that you didn't know before. So let's just quickly review our types of energy. So these aren't all of the types, but it's a pretty complete list. So we've got heat or thermal energy, light, sound, kinetic energy, and electric energy. So you'll notice that these are black. Those are types of energy that are not stored or not potential. Right? You might argue that, oh, you can store heat in a hot object or in water. I kind of see where you're coming from, but we don't think about it that way often. Heat is more of the movement of thermal or kinetic energy within materials, like we kind of talked about in topic 3. So it's more of a transfer of energy than a storing of energy. They won't stay hot forever. The heat will dissipate into the area around them, right? But we have chemical, gravitational, elastic, and nuclear energy, which can all store energy, right? We have batteries with chemical. We can lift an object up, or we can have a lake on top of a mountain with gravitational energy. We'll have elastic or strain, which is like a spring or an elastic band. And we have stored nuclear energy. I'm going to get into that much more in detail shortly. And all of this stored energy can be transformed into other types of energy, right? Either into other forms of stored energy, but more often into these different output types of energy. And most of the time, we'll either want to be creating, well, a light bulb, we obviously want light. Cars will obviously want kinetic, and we need electricity to power homes. So this is kind of going to be the source for these useful energies that we need for our everyday life. And we are familiar with our second, or actually it's our 5th principle of physics, conservation of energy. Energy cannot be created or destroyed, but merely changed from one form to another. So the total amount of energy in the universe stays the same. This is all review. So here's our first new bit of information. We have these cool Sankey diagrams, which are going to show us the flow of energy as it goes from one form to another. And we'll get some practice doing this on a little worksheet. So we can write energy flow diagrams to show the energy changes that occur in a given situation. First of all, we were looking at these brakes of a car. Here's our first example. When we hit the brakes on a car, we get the kinetic energy of the moving car transformed into the heat in the brakes. And you're going to get a little bit of sound, right? And you'll notice the thickness of the lines here is important. We get a lot of heat in those brakes and a little bit of screeching sound. Other example, rocket launch. We got our jet fuel or our rocket fuel being converted into kinetic energy. Right, that's the whole purpose. We're obviously going to have waste as heat and sound. And once it's converted into kinetic, it's going to launch upwards, and we're going to have gravitational energy with a little bit of heat loss, maybe due to friction in the air. Here's a new term for us, and it's kind of self-explanatory, we've got energy degradation. So degradation is a bad thing. We're degrading something. We're taking our nice, pure, awesome energy and we're degrading it. So it's any process, right? It's going to, every process will have some energy degradation. The energy that's transferred to its surroundings, usually thermal energy. We talked about that in Physics 20. Thermal energy is usually our waste energy. And a new term, vocabulary word out there is energy degradation, because it's degrading our pure, useful energy into energy that's no longer available to perform useful work. Right? Thermal energy is just going to be lost into the abyss of the universe. Energy transfer, right? We have transformation, which is from one type to another. Transfer is changing from one object to another. So we can have the energy transfer from our power supply or power station to this light bulb's filament, right? It's actually transferring energy into this filament, which is going to heat up and produce light. All right, here's the Sankey diagrams I was referring to. So you do need to be able to analyze and draw these types of diagrams. They're not overly complicated. It's one of the easier parts of this topic. So a Sankey diagram will show you how much light and heat is produced. We have our starting electrical energy, 500 joules. We're going to have 75 of it converted to light energy and 425 into wasted heat energy. And you'll notice we've got a really large arrow for the large amount of energy. They should be proportional to another. So if it was an equal 250 split, those arrows would be the same size, because the thickness of each arrow is drawn to scale to show the amount of energy. And we need to always have conservation of energy, so you'll need to identify all of the types. It won't always just be two, that the types of energy that you're transforming into, and it needs to have a nice balanced equation of initial and final energy. And again, review of Physics 20, we got efficiency, right, which is going to be our useful output divided by our input. So this is actually waste, so this would be included in our efficiency, the 75 joules. Efficiency is useful energy output divided by total energy input. And you're never going to have 100%, at least in the real world. So you'll always have a smaller number on top, bigger number on bottom, if you just want a little shortcut, right? We got 75 joules of light, which was useful, out of the 500 of input electrical energy. Those two numbers, giving us a mere 15% efficiency. But light bulbs have got better, even better than these ugly, curly, fluorescent light bulbs. We now have our LEDs. But even this ugly I think they're called fluorescent. They're not halogen. We're using LEDs, that's all I know. And it's even better than this. This is 75% efficient. I think you can get LEDs that are over 80%. And here's kind of a different type of Sankey diagram, but it is still a Sankey diagram with the arrows representing the scale of the energy that's being transformed. All right, another new piece of information for you. We got energy density. And just like Sankey diagrams, it's not overly complicated. Just like energy degradation, it's self-explanatory. It's right in the name. Energy density is how dense the energy of our source is. Right? So how much energy can be obtained from a unit mass of the fuel. Right? Just like density is mass per volume. This is our energy per mass. So if the fuel is burnt, the energy density is simply the heat of combustion. That's kind of our simplest way to determine energy density. So here's just some numbers to give you an idea of these different energy densities that are around us. Coal, 30 megajoules of energy. If you burn it, that would be thermal energy per kilogram of coal. Wood would be almost half of that, 16, not very efficient. Gasoline, much better than coal, 47 megajoules per kilogram. And uranium, we've got 70,000 gigajoules, right? So it's actually, what is that, like 8 orders of magnitude more than coal and gasoline. It's pretty potent stuff. It's got a very large, very high energy density. So sugar, coal, fat, gasoline, and then uranium just needs its own scale because literally a gram of this can provide a huge amount of energy through nuclear fission, which we'll look at quickly. Here's a nice cartoon. Log scales are for quitters who can't find enough paper to make their point properly. That's all stacked up. Wow. Hydroelectric energy density. Imagine 1 kilogram of the water in the dam falling 100 meters. Then we're going to lose energy as potential gravitational energy equal to mass times gravity constant times height. So the mass of 1 kilogram of water, obviously 1 kilogram. Gravity, IB likes to approximate as 10, so close enough for us. And the height, 100 meters, we get 1,000 joules. No, that is 10,000. 10 to the 3. And that would be if it was 100% efficient, right? If we could perfectly convert hydroelectric energy into electricity or into fuel, we would get this 10 to the 3 joules per kilogram, which is even less than a megajoule. It's would be considered 1 kilojoule. That actually, would be 1,000 joules. And these are all in megajoules. So hydroelectric energy does not have a very big density. It's 1,000 times less than even sugar. All right, how we actually produce electricity is our next little topic here. This is virtually the same mechanism used for all electricity production, with some exceptions that we'll look at, like solar, but even nuclear and wind and hydro, we're all going to use this electromagnetic induction to create an electric current, and that's going to be used to provide us with electrical energy inside our homes. So what's happening here is a magnet is moved inside a coil and an electric current is induced, and this is covered in depth in Physics 30, so I won't go too far into it, but there's a relationship between a magnetic field and an electric field, summarized as Lorenz's law. And just because we need to have conservation of energy, we're going to induce a current opposite to this direction of our magnet sliding through. But we're going to get a lot more into this in Physics 30. So for now, all you need to know is that when you move a magnet inside a conductive coil, like a copper coil, you're actually going to create a current, and electricity will be the result. So it's induced because magnetic field around the coil is changing, which we call flux. This will all be covered in Physics 30. I'll go through it pretty quick. This is how generators actually work. We're moving coils through magnetic fields. So that in turn produces electricity, an electrical output. Pretty much the rest of today's lesson will be talking about how we actually rotate these coils to produce that electricity. Right? We need to have some mechanical input. And the most popular out there right now, hopefully that will change shortly, is non-renewable energy sources. So these we know are finite, they will run out. They're generally from a form of potential energy released by human action, like mining, like drilling for oil. So we got coal, oil, and gas. All right, the next type we're going to look at would be nuclear fuels, and finally renewables. So nuclear is kind of a category of its own, and we're going to look at all the different types of renewables to some extent, not super in depth, but enough to get you a little more familiar with the physics side of these. So this is an important point. I'm going to highlight the first time. Most of our renewable energy is linked with the sun. We're somehow harnessing the power of the sun and creating energy. An exception would be tidal, which is actually coming from the moon and the gravitational effects of the moon. But other than that, all of our renewable energy is originated from solar, and even I would argue non-renewables originated from solar as well. So the first renewable we'll look at is solar. We have these solar panels, which we are probably all familiar with. This photoelectric effect, which we are not familiar with in depth yet, as it's a physics 30 concept. But in summary, photons are little energy packets of light that are emitted by the sun, or really anything that glows that has light emitting from it. So sunlight will carry, or sunlight in the form of these photons will strike this very specific laminate, which we saw a little bit of in our field trip for the nanoscience for group 4 little project there. So what's happening in a nutshell is this photon with energy is colliding with these laminated materials. That photon is going to transfer all of its energy, or a large portion of its energy, into freeing these electrons, and those freed electrons will now flow through our carrying wire and produce electrical energy as a result. So power from the sun and these photons is being used to free up these electrons and energize those electrons, and those energized electrons will be carried through. So we're not technically turning a turbine with these. We're just shooting electrons with photons. Another type of solar device is for example, is an active solar device. So this isn't a solar panel. We're not producing electricity directly using the photoelectric effect. Instead, we are heating up water or another fluid in these black tubes, right? So we'll get cold water in, and they'll go through these black tubes. They'll get nice and hot, and they will exit our solar device at a warmer temperature. And that could be used to heat your home. I don't think you'd get hot enough to actually produce steam required for turning a turbine, but you could use this to keep your home nice and toasty. All right, we got our wind turbines next. So this one is probably the most obvious connection to what we were talking about with our generators. We have to turn a turbine, which will then provide the mechanical input to rotate our coil around a magnet. That's directly what's happening in these wind turbines, right? You actually have those generators right in the hub of this windmill. The wind provides the mechanical energy to rotate the turbine and spin that coil through the magnet. This one, waves, they're a little bit interesting. This isn't a super feasible way to produce energy. If it were fully developed, it could produce approximately 10% of the world's energy, but it is very expensive. What's happening is the waves are powering this wave capture device, which is going to compress air, and that compressed air is going to go through this turbine, which will rotate it in our generator and produce electricity. But it's not super powerful, as we're only compressing air right inside the chamber. Not a ton, not super reliable, and you can't have these everywhere, obviously. You need to have a lot of waves. We also got tidal, which is similar to our hydroelectric, where we're instead relying on the tides that are a result of the moon's gravitational effect on us. And as the tide comes back out, you're going to have turbines in here, which are going to be rotated and powered as the water recedes back out to sea. And biomass, which leads to different problems with food availability and expense and use of farmable land for energy. But we can produce renewable fuel from these different sources. Corn's a big one, right? Even sugarcane, animal feces, anything that was living and is kind of decomposing, essentially. You can create a biomass or a biofuel out of. So this is a not very current depiction of the world's energy production. We'll just stick with it as an estimate because we don't, for the IB, need to be super precise. So when this diagram was created, we had 40% of the total energy production as oil, 23% is natural gas, 23% is coal, 7 is nuclear, 7 is hydroelectric, and less than 1 as solar and wind and tidal and all of that. Biomass. And as you can see, we have no CO2 emissions from the latter 3, but our first 3 have a lot of CO2, and you'll notice that this coal is especially guilty culprit. So, is very unclean, produces a lot of carbon, and unfortunately, every time you flick your light switch on in Edmonton, 100% of that power is coming from coal. And we need to shift that because that is a very big number, even compared to that. Right? We're getting half as much of the coal and more of the CO2 emission. Not a good ratio. So, with the exception of solar cells, a turbine is turned, which in turn generates electricity. Right? We saw that little diagram. So, you can either use wind, you can use water, you can use steam, you can use air. Any of that is going to be pushed through a turbine, and that turbine is going to rotate through these magnetic coils in the generator, and that's going to produce electricity, and a lot of it. And that electricity is going to go through these transformers. It's going to be converted into more manageable voltages eventually so that you can turn on your house without being fried to a crisp. All right, we went over this already. Here's a little bit more details for each of them. So fossil fuels will always be burned. That heat is used to heat up water and make steam, and then that moving steam will turn a turbine. So that's true for any gasoline, coal, natural gas power plants. We're always using steam to rotate a turbine, and that turbine will produce electricity as a generator. All right, here's a nice diagram. Got coal in, burning it, you're heating up the water. The water is turning to steam and powering this turbine. Turbine is rotating the coil in the generator, which is going to produce our electrical current. Good thing we know how to use magnets, otherwise we wouldn't have electricity. Advantages: fossil fuels are cheap, especially in Alberta where we have a ton of them. They aren't very clean, but that's a disadvantage on the next page. They've got high energy densities. That's good. You don't need as much of them as some other forms of fuel. Variety of engines and devices use them directly and easily. So there's a lot of flexibility, a lot of versatility in these different motors and devices. Extensive distribution network in place already. We have our pipelines set up. We have our coal train sales, railways set up, because it's been around so long and it was our only source of energy for so long. And gas power stations are about 50% efficient, which is actually not too bad, all things considered. The majority of the fuel that we're putting in is actually being converted. Well, not the majority, exactly half of it, according to this, is being converted to our useful electrical energy output. Disadvantages: we can't use it forever. Also, it causes acid rain, and we have problems transporting it. We either have leaky pipelines or barges that spill. We're all familiar with the disadvantages. These are quite obvious, and they contribute to the greenhouse effect by releasing carbon dioxide. All right, here's just a little calculation problem working with some efficiencies and powers. So remembering our efficiency is our useful power output divided by our power input. We want to determine which rate the thermal energy is provided. So that would be our input we're trying to calculate. So we'll manipulate our formula to solve for power input, and that will be our output, which is 400 megawatts, divided by our efficiency, which is 35%, 0.35. We get 1,100 megawatts of thermal energy input into this coal power plant. We need to know the rate that coal is burned at for that, knowing its energy density now. So if it's got 30 megajoules per kilogram, and we're essentially needing to produce 1100 megawatts, where a watt is a joule per second, a megawatt is a megajoule per second. So the mass burned per second is going to be 1.1 times 10 to the 3 divided by 30. Right, we're trying to solve for our mass in kilograms. We got 37 kilograms burned per second. So just to produce these 400 megawatts at this power plant, we're needing to burn 1.2 million kilograms a year. Yikes. And we are revisiting topic 3 here with our thermal energy. So the temperature must not increase more than 5%, 5 degrees Celsius. We want to calculate the rate of flow of water. So this being the final unit in the IB, they have a lot of opportunity to bring all of our previous learning all together. So if we remember here, the rate of the heat loss is going to be our output energy minus our input energy. So that's how much heat we're actually losing, 740 megawatts. So in 1 second, that energy, right, where power is energy over time. So if this were converted to energy, it would be 740 megajoules per second. So in 1 second, we get 740 million, because that's a megajoule. Million joules is equal to the mass times the specific heat capacity times the temperature change. And the specific heat capacity would be given as a constant in either the question or on your formula sheet. So the mass of water required to actually keep our change in temperature to only 5 degrees is 35,000 kilograms per second. Yikes, you need a lot of water. That's another huge disadvantage of coal. All right, off from our non-renewable into what technically is another non-renewable because we have a finite amount of uranium. But it's got its own category because we get to look at some really cool physics of this. This material is almost directly from the final unit in Physics 30. So, little preview for you. We won't go super in depth, but we'll kind of look at it. So, uranium-35 has a large unstable nucleus. No, this isn't chemistry. This is still physics, and physics really is bigger than just equations, right? Chemistry is a branch of physics. A lone neutron is hitting the nucleus. It can be captured by the nucleus, right? So if we shoot one of these neutrons at a nice speed that we'll look at in a second, it will actually be absorbed by this nucleus. And in doing so, it'll change from uranium-235 to 236. So this number here is our atomic mass number. So it's the total protons plus neutrons. Adding a neutron adds a number to that mass number, 236. So the new heavier uranium-236 is very unstable. It's so unstable that it'll split into two smaller nuclei. And whenever we're splitting apart nuclei, we're going to label that as a fission reaction. And in doing this splitting, we're actually releasing two more neutrons. And you can see how this can kind of take a turn for the worse. So we're hitting our uranium-235 with what's actually a slow-moving neutron. It seems like in order for this to actually hit and stick, you'd want a really fast neutron. That's not necessarily the case. In order for this fission reaction with uranium to take place, we need a very specific speed and energy of a neutron. When it is that perfect neutron speed and energy, it'll be absorbed, it'll split, and we're going to produce two more. So we actually have exponential growth of neutrons here. So we are releasing those daughter nucleus. We would call this the parent nucleus, and these the daughter. As the parent split and formed the two new daughter, these neutrons are shot out with much more kinetic energy. So those free neutrons can eventually hit enough things and slow down to the correct speed to actually trigger a nuclear or another fission of uranium-235 into 236, splitting again, right? So those ejected or emitted neutrons are essentially triggers for further reactions to take place. I don't know why these are appearing the same size as the parent. That's not very accurate. Those should be smaller. So if there's enough uranium, right, if we have more of these in place for the neutrons to hit after that initial splitting and ejection of neutrons, so if there's enough uranium, which we consider to be our critical mass is when you have enough for this chain reaction to occur, right? If we have less than the critical mass, right, we're not going to have enough of this starting parent uranium-235 to be split by our neutrons and form this massive nuclear fission reaction. So we have huge amounts of energy being released very quickly, and that energy is coming from not only the ejected neutrons, but also our conservation of mass energy, which is a physics 30 concept. So lots of energy is being released, and it can result in a nuclear explosion. Where's my nuke? What? There we go. So this is what happens with a chain reaction. Tons of energy, super fast. Pretty much all of that uranium is consumed in a very short amount of time. In a big chain reaction. I'll post that video if you want to watch more. All right, so that seems dangerous, right? We don't think of that as being a very good thing or good idea. But if the chain reaction is controlled using control rods and a moderator, then we can actually keep this chain reaction from overwhelming the system and causing a Chernobyl to happen. So I recommend you take the time to watch Chernobyl on HBO. It's a little bit gruesome, but it'll actually teach you a lot about the physics and the moral nature of nuclear energy. I really enjoyed it. I think you guys would too. So if you have time this summer, that would be a good way to get ready for Physics 30 and to have a lot of fun in the process. So the energy can be used, right, instead of as all being a big explosion all at once, we can actually harness that energy to generate electricity. So our fuel rods will have enriched uranium. So naturally, uranium is not most commonly found as uranium-235. I think 238 is the normal. But if you have a larger percentage of uranium-235 in your fuel rods, you're going to have more fission taking place. So how they do that, they essentially take all of their uranium and they throw it in a big spinning centrifuge, and they can separate it based on its atomic mass. So you can get the stuff that you want in your fuel rods, the enriched uranium-235. All right, we also talked about a moderator. A moderator slows down the free neutrons, making them easier to absorb by their uranium-235. So the most common moderators is graphite or water. So you actually need 1 electron volt neutrons. That's the energy of the neutron. So they're actually moving really slow. And in order for them to be traveling at that speed, we're going to need to slow them down using control rods and moderators. And once they are at that controlled speed, they'll hit another uranium-235 parent atom and cause a fission reaction and create 2 new neutrons, which will be really fast and need to be slowed down again by the moderator. So control rods will absorb the excess neutrons, right? Because every time we're splitting one uranium-235 nucleus, we're going to create 2 neutrons. So we have to do something with those extra neutrons, or we're going to have an out-of-control chain reaction. So boron is normally used as the control rod. It'll absorb those extra neutrons in a safe way. So the moderator is used to slow down neutrons so they can actually be used to trigger the fission. The control rods are used to remove the excess neutrons so we don't have too much happening at the same time. And this is where our problem comes in for Chernobyl. An error in the design and the execution of these control rods, these boron rods. And I won't give you any more spoilers because I really think you would all enjoy it and learn a lot from it. So moderators get hot from the energy. Oh, it's so hard to not give more spoilers for Chernobyl. It gets hot from the energy it absorbs from the neutrons. And that heat is then used to heat up water via an exchanger. So it's actually the moderator, right? The combination of our water and our graphite. Most likely the water, right, is going to be heated up to a really high temperature and then put through this heat exchanger, which will make steam. So the water won't be exactly boiling in the reactor. It might be, but it'll be brought into this heat exchanger, which is going to transfer the thermal energy from the moderator, from the water that's been heated up by the nuclear reactor. And that steam will be again forced through the turbine, which will generate electricity. And they'll need to cool it, right? That's where you see these big nuclear cooling towers that all the nuclear sites are famous for. That's actually to keep it from blowing up. The reactors are in this containment structure, often with meters and meters of lead and concrete around them. So if something did go wrong, it would be contained. So nuclear is actually safer than you'd think. Useful byproducts of uranium or of nuclear fission reactions. The uranium-238, which is the more common, not the enriched fuel, in the fuel rods can also absorb neutrons and produce plutonium-329. So while our main event is happening with the uranium-235 and our neutrons, some uranium-238 will also absorb neutrons and form plutonium-239. And that's another nuclear fuel. So we can kind of create more fuel as we're doing this and then use a different nuclear reactor, a breeder reactor, which is going to be fueled instead of by uranium-235 by plutonium-239. And the process would be very similar, not quite the same, but you're getting a useful byproduct. It makes more fuel. That's very nice. It also has a really high power output. We looked at the energy density of our uranium compared to all of our other sources. It is insane how much that stuff packs a punch. There are large reserves of nuclear fuels, especially in Saskatchewan, believe it or not. I think that's either the largest or second largest deposit of uranium. So there is a lot more of it than you might think available to us, and it won't produce any greenhouse gases. The disadvantage, the waste products are dangerous and difficult to dispose of. You essentially have to bury them in giant concrete containers until they eventually settle down, have no more nuclear reactivity to them. There's major health hazard if there's an incident, as you can see in Chernobyl if you take a look at that and watch people's skin essentially melt off or watch them bloat and die from the radiation poisoning. There's problems associated with uranium mining. there's environmental impacts with all mining, and we get the potential for nuclear weapons to be created if this uranium that we're intending for nuclear power, if it ends up in the wrong hands, we can have a big problem on our hands. And it's also very expensive to build and maintain. Solar power, right, we have our photoelectric effect from our photovoltaic cells, and we have this active solar devices, which are just heating up water. Let's look at the solar constant. The sun's total power output is 3.9 times 10 to the 6 watts. That is a lot of power every second. Kind of unimaginable how much that is. So only a fraction of this power actually reaches the Earth. And we can get that formula from our intensity, which we looked at in topic 5, or topic 4 actually. So the power per unit area is equal to the total power divided by 4 pi r squared, the area of that sphere that is the Earth, essentially. So for the Earth, we're only getting 1,400 meters or watts per meter squared. That's our solar constant here on Earth. So this solar constant you don't need to memorize, but you do have to understand what it means and how you can use it to solve problems. You also have to understand that that solar constant, right, power per meter squared of the Earth's surface, varies according to the power output of the sun. That's not a very big difference, 1.5%. So I don't know if that's more or less talking about solar flares or the activity of the sun at that given moment. And the distance from the sun. So the Earth has an elliptical orbit around the sun, so different times of the year we're further or closer to the sun. And a final effect on the solar constant is the angle of the Earth's surface, or the tilt. So this means that our solar constant, our 1400 watts per meter squared, can only shine across on the cross-sectional area of the Earth as seen from the sun. Right, so we're always going to have half of the world black. So the cross-sectional area of the Earth is pi, because we're working with a sphere, times r squared, where r is the distance to the Earth. However, as the Earth turns, this is spread over the total surface of the Earth, which becomes 4 pi r squared. So the average intensity of the sun falling on the Earth is pi r squared, where r is the distance to the Earth, and we're dividing that by the total surface area of the Earth, which is only 350 watt per meter second. So this is kind of just taking into account the shift from day to night and the total surface area of the Earth. So that's essentially what we're working with as an average intensity at any place on the Earth, which is still a fair bit of energy, but the problem comes from us not being able to harness all of that effectively. So solar power is free once built. You've got no fuel other than the sun, which is there and it's not going anywhere. It's renewable and it's clean. Disadvantages: it only works during the day. It's affected by cloudy weather. We've got low power output, requires large areas, and it's very expensive. Another one that I would put there is that because it only works during the day, you need to store power for at night, and we don't have batteries that can do that to the extent that the world needs. All right, hydroelectric power. We're storing water in lakes. Water's entering the lakes from rain and snow on mountains. The high water has gravitational potential energy, GPE. Once it falls through the dam, it's going to be transformed from gravitational potential energy into kinetic energy, and that kinetic energy is going to turn the turbine. So we've got kind of three different, or I guess, yeah, the main one is water storage in lakes. That's what is most common. A second form of hydroelectricity is pumped storage. So this is where excess electricity can be used to pump water up into a reservoir. Acts like a giant battery. So any extra electricity, if we've got an overflow of water coming out, we're actually going to use some extra energy that we can't send to the grid back up into the reservoir. So this is acting like a battery because we are saving that water for later now, and when we need it on a rainy day. And we got tidal water storage, which is trapped behind a tidal barrage, and it's going to turn the turbine both on the way in and on the way out. So it's going through these kind of narrow channels in those big concrete tidal barrages that we saw a picture of earlier. That one's a dam, but as the tide shifts with the moon, it's going to move with some kinetic energy, and that kinetic energy is going to turn this turbine and generate electricity in the generator. Goes both ways, which is quite impressive. So again, hydroelectric, very similar advantages to solar. It's free once it's built, it's renewable, it's clean. Our disadvantages, you can't build them anywhere, right? Edmonton's not great for it unless we start throwing turbines in North Saskatchewan. It also creates drastic changes to the environment, which can lead to flooding of farmland or even collapses that can devastate communities and kill thousands of people. And it's extremely expensive, right? If any of you have been to the Hoover Dam, you can see the scale of that and how expensive that must have been to build. So wind power, it's just air flowing through a turbine. Here's an example of how we can calculate it. We want to find the cross-sectional area of the turbine because that's what's being affected by the wind. So wind traveling at a speed A with this cross-sectional area A. We can find the volume of the air going through the turbine per second by multiplying our cross-sectional area and our speed of the wind. The mass of the air per second will be the density times that volume, and the mass of the air per second would be combining those two: density, cross-sectional area, speed. So if all of the kinetic energy is transformed by the turbine, the amount of energy produced per second is half of mv squared, where we actually have the mass as density, area, volume, or speed. So the amount of energy produced in a perfect wind turbine would be half of that density, cross-sectional area, speed cubed. So hopefully you'll be able to derive that equation on your own if a question came up, just going through that understanding of cross-sectional area, speed, density. The advantages, again, it's free once it's built, it's renewable, it's clean, and it's good for remote locations, right? You're not dependent on very specific locations like solar and wind would be. Actually, you are determined. You need to be in a windy place, but you don't need a lake or a river or the ocean. So disadvantages, it work only if there's wind. Some days there just won't be wind. There's a low power output. We're not actually producing a ton of energy. They are unsightly. Some people don't like the look of them. And noisy. That's a big one. People often complain about them killing birds, but cats kill like a million times more birds than windmills, and nobody complains about cats. So I don't like that argument. Don't use that argument. Windmills don't kill cats or birds. Cats do. High maintenance costs. To fix these, it's very expensive. You actually have to replace the generators frequently. So we're using a lot of minerals, and there's a lot of environmental impact just from the repairs. All right, wave power. This is a less known one. We have an oscillating water column, which kind of traps the wave inside of this uniquely shaped and designed column or chamber. That's going to produce higher air pressure. It's going to compress the air, shoot air through a turbine that's going to spin, and as it spins again, it'll power a generator. So it'll again, like our other tidal energy, when the tide comes in, it's going to turn the turbine one way. When it goes out, it'll turn it the other way. And if we've set up our generator to kind of work on a switch like that, we can continuously produce energy as long as the waves are coming in and out and rotating our turbine. So we need to be able to actually determine how much energy there is in a wave using a nice assumption, a nice simplification of waves being rectangular waves. So if our waves actually look like this, which on average they're not too far off from that, we can simplify it by modeling as a square. We can find out how much energy it has, thinking about it as gravitational potential energy. So the water above this center line, right, it's all lifted at some height, and if it drops, it's going to convert gravitational potential energy to kinetic energy, and that's where we are able to calculate the energy in these waves. So if the shaded part is moved down, C becomes flat, right? We want to find the mass of the water in the shaded part, so we need to find the volume and the density. So volume would be the cross-sectional area of this wave times half of the wavelength, the length of it. Sorry, that's not cross-sectional area, that's amplitude. So A is the height of the wave, and then we've got the wavelength over 2 as the width, and the length is L, the length of the wave. And we're going to need to multiply that by the density to find the mass. The loss of potential gravitational energy is equal to mass, which we just solved for, times gravity times height. So mass, or amplitude, wavelength, length, density over 2, times gravity's constant, which IB uses as 10. We use as 9.81 in our Alberta courses. And the height that it's raised at is the amplitude, which is kind of a weird approximation, because I would use half of the amplitude, because only the very top of the water is a full amplitude above it. But we'll keep going with what the IB tells us. We'll use this approximation that it's at a height of A above, I guess, yes, because this bottom section of the wave is still going to travel the full length A, just as the top will travel the full length A until they become flat again and have no more gravitational potential energy. So that's the height. We have the loss of gravitational potential energy, mgh. We can simplify it, right? mgh. We have now a squared, gravity's constant, length, radius, wavelength over 2. And that's per every wave, right? We want to know the number of waves passing in a unit time. So waves per second would be our frequency, just like a hertz, like, yeah, a cycle per second, which can be used using the universal wave equation, speed of the wave divided by our wavelength. And we can actually get rid of the wavelength in our formula using that substitution. Right, we got wavelength on the denominator and on the numerator. Those will cancel out. We're left with the final equation, the loss of potential gravitational energy per unit time is equal to half of the amplitude or the height of the wave squared times the length of the wave times the density times gravity times the speed of the wave. And if you want to find it per unit length, obviously all you need to do is divide by the length. Divide by length, and we get this new maximum power available per unit length equation. So power per unit length, these questions just be simply plug and chug as long as you're able to remember or calculate this formula. So we got advantages, again, just like solar, wind, tidal. It's free once it's built. Reasonable energy density, so it's a little more bang for buck than some of our other renewable sources. And it's clean, but we can't use it anywhere. We can only use it in areas with large waves, otherwise we would have low energy densities and it wouldn't be worth building. Waves are irregular. You can't count on this for constant supply of energy. We have low frequency waves with high frequency turbine motion, which essentially means that our waves aren't always coming in fast enough to turn the turbine. The maintenance and installations are really high, so it's an expensive endeavor. We need to move this energy from the shore to where we need it, so there's going to be extra transporting power involved, and it needs to withstand storms and hurricanes. These need to be durable and well built. Alright, that's all we got for today. It was long, but we are over halfway done this PowerPoint. We'll finish up next week, starting off with Stephen Hawking's insight on radiation from the sun. Alright, thanks for sticking to it. Maybe you want to do some extra research on your own. Who knows? Hope you enjoyed. See ya.